Okay, so this is the last talk of this workshop, and we have Costas to tell us about marginal deformations and quasi-Hopf algebras.
All right, thanks, and thanks to the organizers, in particular Vishnu, for having me talk at this workshop. So some of you might have heard versions of this talk before. I've been kind of giving incremental kind of progress reports on this project for a couple of years. What I did, since we're kind of, it's the last stop of the workshop, I removed a big chunk of the slides, of the more technical ones at least. So hopefully it will be a kind of light talk and we'll have enough time for lunch. Okay, so this work is based mainly on this paper with my then master's, now PhD student, Hector Dlamini, and some work which should appear in the coming weeks. So it's okay. Before I get to that, I mean, let me, since also we have people visiting South Africa for the first time, Pretoria is this place not very far from Johannesburg, which is famous. Okay, the quality is not good, but it's famous for its jacaranda trees, which are of course from Argentina. But they were planted there back in the late 1800s and bloom every year in October, and they make a very nice sort of scenery for the city. If this moves, okay, so this is just a view of the campus. So some of you might have already seen the Wits campus. Pretoria is kind of similar. Okay, so let me now go to the talk. So what I want to do here quickly is discuss the symmetries and integrability of the exactly marginal deformations of n equals 4. I'll specify which one specifically I'm thinking about, and explain why, to understand these symmetries, it's useful to generalize from Lie algebras to what I'll also define as a specific kind of quasi-Hopf algebras. These will be defined using a Drinfeld twist, and this twist I'll use it to define a star product on the representation space of these algebras, which I will claim might provide us some interesting insight into these theories, and in particular the integrability or not of some of these theories, and also perhaps some insight, as I will very quickly explain. These are the slides I removed on the gravity dual of some of these exactly marginal deformations. So okay, so let's go back to n equals 4 to the beginning. Of course, I don't need to spend too much time on this slide. N equals 4 is the unique four-dimensional gauge theory that has the maximum local supersymmetry. And it has all these beautiful and interesting properties. In particular, okay, it's perturbatively finite, as was already known in the early 80s. It has also non-perturbatively finite. It plays this major role in the ADS-CFT correspondence. It's planar integrable, also its planar amplitudes have very interesting features. The question is, is it the unique theory that has all of these features that are so special, or it might be, are there theories which share some of these features, not all of them, and how does this knowledge that we've accumulated over the past years for n equals 4 can that help us to understand more realistic theory? And the particular theories I'm thinking of is those that are as close as possible to n equals 4 without being n equals 4. And for that, I would like to preserve conformal invariance. So I'm looking at marginal deformations. And the ones I'll be looking at are these theories that you can obtain by doing superpotential deformation, which by itself, if I do that, I preserve n equals 1 supersymmetry. So if you go to n equals 1 superspace, which I'm not going to really review now, so this is you're at the Lagrangian superspace, so it depends on the chiral superfields of the theory, and of course the vector. There's the vector part, so there's the symmetric term, these are the interactions. So all I'll be doing is changing the interactions away from the superpotential of n equals 4. So in the n equals 4 superpotential is written in terms of 3 scalar superfields, or chiral superfields, in this way. And I want to think of, first of all, the most general classically marginal deformation I can think of, which of course has to preserve the cubic property of the superpotential, otherwise it's not classically marginal. And also this H needs to be a symmetric tensor. Now, out of those, of course, not all the deformations are going to be exactly marginal. Some of them will get quantum corrections. The function is going to turn on and they'll become non-zero. Perturbatively, but then eventually non-perturbatively by Leigh-Strassler, it was shown that this particular subset of those think it was like 10 deformations. Now, if you focus on only these ones, which are actually essentially only two, where you turn on this Q and also this H parameter. Q is a deformation of the commutator that was there in the previous. So if you look here, there was a commutator. This is n equals 4 case. Here now we have a Q commutator, and you also introduce this cubic term. And the statement of Leigh-Strassler was that by studying the anomalous dimensions using the NSVZ beta function, that there is a combination of the gauge coupling, G, of this kappa that used to be G, but now it can be different, Q and H, so there's a function of all those, unknown in general function, for which these are exactly marginal. Now, you can calculate this at 1 and perhaps 2 loop orders, and this function kind of looks like this to one loop. And as you can see, there's actually one more parameter here which I did not write, which is the rank of the gauge group. So it also depends on the rank.
So Q is a phase or is general?
No, Q is I'll keep it general. Of course, if it's a phase, which is this case here, which I call interesting, then so if Q is a phase and H is 0, so we drop this term and Q just make it a phase, then this is known as the real vector deformation, and it has many interesting properties which in general are not there. But that will not be the focus of my talk.
In this case, with H equal to 0, the viewer is looking at a background. Is it still unknown what it corresponds to depending on H?
Yeah, it's not totally unknown. I mean, it's known to second order in H, like you can perturbatively construct it to do some order in H, but still unknown. So many people, it's a hard to crack problem. Many people, including Aharoni and friends, and I'll be mentioning very briefly perhaps some work by Manuela Colaxisi, who back about 10 years ago worked on this problem and got some results. But yeah, there is no known, and I'll explain why there is no known background. But that is perhaps one of the major goals of what I'm talking about. Can we perhaps figure out the background? Okay, so n equals 4 is just this thing. If you put q equals 1, h will be 0, and this kappa automatically from this function will end up becoming the same as the gauge code. So how do these theories compare with n equals 4? Well, n equals 4 is conformally invariant, so these theories for any q and h should be conformally invariant as well. N equals 4 has an ADS-CFT dual, which is ADS 5 versus 5. For complex beta, so if you take Q to be the phase, but then you make beta complex, which means Q is general, essentially, it doesn't have to be a phase, then the background is known. It was discovered by Drinfeld Twists. And the way they produced it, I think, is well known. You do these TST transformations. So I'll say a few things about it, but you take advantage of the fact that if you drop this term, this has a lot of symmetry. In particular, it has lots of U1s. There are 3 different U1s. You can use one of the U1s actually one of the U1s you don't want to break because that's the R symmetry. But then you can use the other U1 to do a T-duality. Then you can use the third U1 to do a shift, and then you can T-dualize back. That gives you, of course, you can only do this shift if beta is real, because it's actually a real shift of an angle. But then what they did, they did the SL to R transformations on that real beta background, and they got the full complex beta background. So TST was part of the picture, then you did the SL to R. Now for planar integrability, it turns out, and this has been studied from the spin chain side as well, back from the early days, in particular Bernstein and Cherkis, for instance, studied this, and they found that essentially, and this basically I will quantify it later, but essentially you only get integrability, so basically you can map this to an integrable spin chain only for real beta. If beta is complex, it turns out not to correspond to any known integrable system. And also in other work, which I'm not talking about today, we use this analytic non-integrability approach that I kind of maybe mentioned to Diego a bit earlier. We use this to study strings on this complex unidimensional background, and showed that, at least according to this technique, the Hamiltonian system you get, it does not admit Liouvillean solutions. So from that perspective, it's not integrable. Well, we could not show that for the real beta definitely. Of course, there is a Lax pair for real beta, so we know it's even the sigma model is integrable. So basically, real beta is kind of important, and it's the only sort of known integrable case. And this basically means that actually, well, you can start from real beta, and you can do some kind of unitary definitions of the fields, and you can get theories that look much more general than real beta. So basically, you can turn on this part. Sorry, if I go back. Okay, so you can turn on this part by starting from real beta and redefining your field, so you can turn this on, but of course H will be related to Q. And those can also be shown to be as integrable as the real beta case, but of course I don't consider them as a really new case. They're just unitary definitions of real beta. So anyway, what I want to do first is look at these symmetries a little bit more closely. And just at the level of the classical Lagrangian, so okay, what are the symmetries of N equals 4? Okay, we all know it has the superconformal symmetry. I'll focus only on the R-symmetry subgroup, and in particular, the SU3 times U1 way of writing it in N equals 1 superspace. So the reason it has this symmetry, this particular, let's focus on the SU3. The U1 is kind of implied by writing it in terms of superfields, but in this way of writing it, this is how the superpotential looks, and epsilon ijk is the invariant tensor of SU3. So if I do an SU3 transformation, where U now is an SU3 matrix, and I transform phi to U phi, then of course this is going to give me the determinant, and this is 1 because it's SU3. So that's how I know that this has an SU3 symmetry. Okay, it's so something very simple. Now let's look at this. This is the Leigh-Strassler superpotential. What are the symmetries of this? Of course, it still has a U1 because it's written in terms of the Karl superfields. Is there anything else? Well, there are some obvious discrete symmetries you can think of. For instance, you can take phi1 to phi2, phi2 to phi3, that's a Z3, and that is invariant. Indeed, this was actually a crucial, actually both of them, but especially this one, these were crucial symmetries in deriving this form of the superpotential. That's what Leigh-Strassler used to state that all the anomalous dimensions are the same. And then you can put them to 0 and show that this is superconformal. So these threes are very important, but they're discrete symmetry. There's also a third Z3, which Aharonian friends showed back in the days that these form a particular discrete non-abelian group. But still, I mean, these are discrete symmetries. Now, for real beta, actually, even for complex beta, this doesn't matter so much. I mean, this term drops out, and you just have some U1s. So the question is this all? Are these all the symmetries that we have? Just the U1 and some discrete symmetries? Because that's the real problem in constructing a solution generating technique. If you have the U1s, you can do what I discussed a bit earlier, do T-dualities. Here, you don't really have anything apart from the discrete symmetry, so you cannot T-dualize and do a TST type. Okay, back in about 10 years ago, what we showed was with Theresia Monson that this global SU3 that was there for N equals 4 is not really broken. If you change your perspective slightly, you can write it as, you can actually think of it as being deformed to something known as a Hopf algebra, which I will define in the next slide. So the way we're thinking about this is take these phi's. Now remember here, I was transforming phi to U phi, or this is an element of SU3. Now I'm doing the same. I'm deforming phi to T phi, and T is a 3x3 matrix. Well, these are the elements of the matrix. But this is not an SU3 matrix. Why? Because these T's are taken to satisfy these relations here, and which, if you write them down, you can specialize them to specific ones. But what this is telling us that, for instance, T11 times T12 is not the same as T12 times T11. It could be, for instance, that T11 times T12 is Q times T21 times T1, or T12 times T1. So basically, I'm not talking about non-commutativity of the matrices, of course that's always there because it's SU3. I'm actually taking the elements of the matrix, the components, and I'm saying that these are not C numbers anymore. These are some operators which satisfy commutation relations. And if they're specifically those commutation relations, now A's and C's are, this can be 1, this can be 2, I mean, you can write the whole set down. So if they satisfy these specific commutation relations, then what you get is that this thing stays the same. Okay, so we get invariance of this superpotential.
Say Q was -1, then this thing is, this matrix is now a fermionic matrix?
Let's see, so Q is -1. Well,
that changes the commutator to an anti-commutator. So is it true that then now
yes.
T is a matrix of fermions? Of
okay, that's
Grassmann
actually,
variables?
I'm not sure. I mean, I would expect that, but I'm not. So you win H equals 0 and H equals 0 and
yeah.
Q to be -1.
Yeah.
I mean, my problem is that we always think of Q as close to unity. So now you're maximally far. Like I'm always thinking of this. Okay. I have to
there
quantify
are
what I'm
also
saying.
Q squared there, right? So
Sorry?
there are terms which go like Q squared.
Yeah.
So, yeah.
No,
I mean, it would mean just not the normal anti-commutator, right? I mean, with the anti-commutator.
No, the commutator in the Lagrangian becomes
there's
the
a minus here
anti-commutator.
and, yeah.
That's just the fact, right? In the Lagrangian, it's just changing commutator to anti-commutator.
No, I think
so
that's
I'm asking what it does here.
Yeah. Okay.
I see what you mean. I see what you mean, but
okay, there is a problem which I think what you're saying is probably very, very close to being the case. The problem is that quantum groups are, notoriously a little bit suspicious at roots of unity. So Q equals -1 is a root of unity, and I'm explicitly not talking about that. I'm talking about the generic case that, at least in what I'll discuss now, I'm talking about the generic case where Q is 1 plus some small perturbation.
But so this transformation changes the statistics of the field, right? Because now the new phi is multiplied by elements of some algebras non-commutative.
Yeah, you can think
So the new phi is not...
So there's some braiding in general, and yeah, perhaps for Q equals -1 you get some actual fermionic statistics, but I have not studied that, which is an interesting question.
So the reason I'm asking this is this is not interfering with the unitarity or anything like this?
Okay, so can I defer that question to a little bit later, because there is I want to make statements about quasi-Hopf algebras, and maybe then I can come back to this question about unitarity. Not that I have too much to say, but at least I refer to the literature based on it. Because actually this is not what I want to talk about today. I'll have a different dual description of what I'm talking about there that I think is more powerful and more useful for what we want to do. So you'll see how that's around. Anyway, just to discuss a little bit what these constructions are. So we know what of course we know what an algebra is. The main part of an algebra is that you can take 2 copies of your space and get 1 copy using this map or the multiplication. And you can also have a coalgebra which has the opposite thing, a coproduct, which takes a single copy to 2 copies. And there need to be some consistency relations between all these and units and co-units. And if these are compatible, so both the product and the coproduct are compatible in a specific way, so basically you can invert the arrows, then you have a bi-algebra. And the Hopf algebra is a specific kind of bi-algebra which has an antipode, which is basically the generalization of the inverse element. So there's some invertibility. And now the coproduct, just as a reminder, what I mean is, well, for a Lie algebra, the coproduct is something trivial, and that's what you all know from quantum mechanics. When you take the coproduct, suppose you have a 2-particle state, and you apply the coproduct of the spin operator, well, that distributes in this nice way that the spin acting on the product state is the spin of the first one plus the spin of the second one. Okay? And that is the quantum mechanical statement of this thing here. And the important thing about this, and as well as this is commutative. If tau is the operation which exchanges my 2 copies of my representation space here, or actually here of my algebra, because these are algebra elements and these are the modules, so the representation. If you exchange it, you get the same. Now, if you make this non-commutative, if you make the coproduct non-commutative, for instance, you could add a Q, for instance, here instead of a 1. That's makes it be non-commutative. Then you get a Hopf algebra. And this is kind of the very sort of physics definition. Of course, I'm not giving many of the mathematical definitions here. I'm skipping most of them. Now, one way, a very productive way to construct Hopf algebras is using RTT relations, which are basically these. Take a matrix R, which lives in 2 copies of the algebra, and these T's are your generators of your Hopf algebra, and if you, given an R matrix, if you can find T's which satisfy these relations, and on top of this R matrix that you choose satisfies this quantum Yang-Baxter equation, then you have a consistent Hopf algebra, and which, because of this, is actually not too trivial. And let me say a few things about this. Well, what's the point of this relation? Well, see, you're defining here some relations, some quadratic relations between your T's. Now the question is, what happens at the next level? Suppose I look at cubic relations. Now, do these, suppose I calculate some cubic relations based on the quadratic ones. There are several ways of doing this. If you assume that your algebra is associative, that imposes constraints, because there are many ways of doing it, of putting a parenthesis. So, and I'll say more about this in a minute. But if you have, if at the cubic level you have 2 ways, at the quartic level you have more, and associativity will place constraints. The danger is that those constraints will trivialize your algebra. The only solution will be that the T's are 0. Okay. And you don't want that, and what FRT showed is that if the Yang-Baxter equation is satisfied, then this algebra is not trivial in that sense. Okay, so associativity, which is very related, of course, to the Yang-Baxter equation, holds, and so there's no new relations at every order, cubic, quartic. And this is actually exactly what we did. So back in 2008, so those funny relations that I showed you, these ones, we derived them from a given R matrix of these Leigh-Strassler theories, and we just applied the RTT formalism, and we got these. And then checked that the classical superpotential is invariant at okay, just to say one more thing in this kind of construction, the R matrix controls the non-commutativity of the coproduct. So remember now, if you want a non-trivial Hopf algebra, you want your coproduct to be non-commutative, right? Otherwise you go back to the Lie algebra case. So there's a relation like this where the coproduct of some element, if you invert it, it's actually not the same as what was before you permute the copies. It's actually a similar transformation with respect to this R matrix. So the role of the R matrix is to control the non-commutativity of your coproduct. And there are, of course, many. I mean, it's a huge field of Hopf algebras and quantum groups, which I'm not going to really say too much about. But the only last sort of piece of formalism I need is that there is this concept of a Drinfeld twist, which says that given a Hopf algebra, you can twist it using an element which also acts on 2 copies of the algebra, and you can take the old coproduct, which for instance could be a commutative coproduct, and make it non-commutative by twisting. And if you do that, then you also get a twisted R matrix, like this. So if I give you an original R matrix and you want to get a new one, then you can twist it using this element. And the important thing about this is not a similarity transformation, right? Because the reason is that here I've actually changed the 2 copies of the algebra. If this was 1, 2, so this notation means this lives on 2 copies of the algebra, and this is the inverse of the 1, 2, but this is not the 1, 2, this is the 2, 1 component. So there's something else happening here, and that's why this is non-trivial. Otherwise, of course, just a similarity transformation, and nothing you would expect to happen. Now, if you want this process to start with Hopf algebra and get the Hopf algebra, there's an extra condition which is called the co-cycle condition, which I kind of abstractly write like this. I'll give explicit expression for some of these things a bit later. But anyway, so this one can think of as an analog of the Yang-Baxter equation. Okay, so what this implies is that the R matrix, I'm not going to show this, but it implies that the R matrix satisfies the Yang-Baxter equation. Now, quasi-Hopf is what happens when you consider more general twists. They need to be invertible, and maybe they have a few other conditions, but the main thing is they don't need to satisfy this co-cycle condition. So the R matrix does not satisfy the Young-Baxter equation. And what that means is, there's two perspectives on this. Either you impose associativity on your cubic level expressions, and then you see whether that trivializes the algebra, or you just forget about preserving associativity and say that, well, actually, I don't necessarily need to have my two possible placements of parentheses to be equal. Okay? And that's the perspective we're going to take now. So the reason that this is kind of useful is because even though this is now the expression of non-associativity. You see here, I'm first doing the, well, okay, this I'll quantify it a little bit later. I'll write it in indices so that it kind of makes more sense if one is not familiar with these kinds of expressions. But what this is one way of placing the parenthesis, and this is another way of placing the parenthesis. And they are related through an object called phi, which is defined down here. Okay, it's a slightly messy definition, but I mean, it makes perfect sense if one thinks about it a little bit carefully. And so basically, even though these algebras are non-associative, and non-commutative as well, so the coproduct is non-commutative, but it's also not co-associative, because this is talking about the coproduct, not about the product. The product is the usual, in this case, would be just the usual matrix product. So that's always associative, not commutative. But now talking about the coproduct, and then what you have is that, well, actually it's non-associative, but it's under control. If I give you any expression with the parentheses organized in one way, you can write it in the other way using the coassociator. So they're not equal, but you can go from one to the other. In the same way that the R matrix can take you from one ordering to the opposite ordering in a non-commutative algebra, the same for a non-associative algebra. And now, what happens is now that your R matrix here, that you get by twisting, so basically exactly the same thing here, does not satisfy the Young-Baxter equation. It satisfies the quasi-Hopf version of the Young-Baxter equation, which is this, in terms of the same phi. Anyway, these are my definitions. Now let's go back to the Leigh-Strassler theory. Now, I'm going to read off from the Lagrangian what is my one-loop spin-chain Hamiltonian. And this is it. Okay, so what have I done here? This is a Hamiltonian acting in the scalar sector. So I'm organizing my scalars here in a basis where you have phi1, because it acts on two copies, right? The Hamiltonian, it's a nearest neighbor Hamiltonian, it acts on two copies and gives you two copies. I mean, two scalars, and it gives you, as an output, two scalars. So this is acting on phi1, and I have my basis 1, 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. So basically it's a 9 by 9 matrix. Okay, that's why this is 9 by 9. And you can see where everything goes. Now, this thing, if you were to go to n equals 4, sorry, then what you would find is that this becomes 0, this becomes some phase. Actually, this becomes 1, because for n equals 4, q is 1, q bar is also 1. And you get something which you can write as 1 minus a permutation, which is the usual Hamiltonian, one-loop Hamiltonian of n equals 4. Okay, so this just generalizes that thing. And from the Hamiltonian, I'm going to construct the R matrix. And let me just emphasize here, when I'm talking about the R matrix, it's perhaps not the R matrix that some of you might know from integrability. What it's lacking is a spectral parameter. Right? So this is not the dynamical. I'm not looking for a solution of the dynamical Young-Baxter equation. This is at the quantum group limit, where I've taken the spectral parameter to infinity. So it's only the parts which are, somehow a more a simplified version of the Young-Baxter equation, but which is actually more related to the quantum group structure, the algebraic structure behind. Okay, so this R, this is the R matrix that will be our object of study. It does not satisfy, in general, the Young-Baxter equation. And that's how we started thinking about all this business, because, okay, of course, that's the statement about non-integrability of these Leigh-Strassler theories. If you take real beta, for instance, then it does satisfy the Young-Baxter equation, and that's an integrable deformation. And all the other known integrable deformations were found in this way, by looking when does this satisfy the Young-Baxter equation, and then you find some deformation, and then you find that all of them are actually related to real beta by some unitary definitions of fields. So there's only really the real beta is the only non-trivial solution here. But what we want to do is something more general. We want to look at the full R matrix and derive it from a kind of twist. Okay, and see, can we actually derive this from a twist, and does it tell us anything about these theories? And that's going to appear in the next page. So we found a twist, and this is the unpublished work. I'm moving now to the current results, which actually produces this general R matrix, starting from the trivial R matrix of n equals 4. Now in this language, the R matrix, there was some permutation happening when they defined the R matrix from the Hamiltonian, but for n equals 4, the R matrix is just identity times identity, if you take the spectral parameter to infinity. And that is essentially 1 minus permutation, and because the Hamiltonian that you get from this would be 1 minus the permutation, so the usual Hamiltonian. So this looks like this, and you can see there are several parameters here, A, B, C, up to J, and they're all on the next page. So that's how the twist looks in general. Actually, maybe I skipped, maybe J has been cut off, but anyway. But you see the structure. They're not very simple expressions, but actually they're also, this is a slightly complicated way of writing them, because in a way, obviously, we only have like 4 parameters that we can deform by. So we have Q, Q bar, H, and H bar. These are our deformation. This is our conformal manifold for these marginal deformations. So that means that actually we should not really expect these to be totally independent quantities, and they're not. There are relations between them. So I don't know, there are some relations like A minus C bar equals to E, or there are the relations like these. Okay, so these are not totally independent, of course, because there's only 4 parameters. Q, Q bar, H, and H bar. So anyway, we have this twist, and it has some interesting properties. In particular, the R matrix is given by this. That's the twist. But now we start from the initial twist, which is the R matrix of n equals 4. And so here there should be an R matrix, which is the original Hopf algebra, but that's a Lie algebra, because what I'm actually doing is deforming SU3. So the R matrix of SU3 is just identity times identity. From this perspective, because the coproduct of SU3 is trivial, is the commutative. So what I'm doing is I'm taking the SU3 R matrix and deforming it in this way. And it also has some property called the triangular property, which looks like this. And for known cases which are integrable, for instance, for the real beta, Q equals E to the I beta, but beta real, this becomes a Hopf twist, meaning that it satisfies this co-cycle property. Also, in previous work, we have studied quite extensively this theory, which we call the W deformation, where W here is a real parameter. So this is a theory which is related by unit transformations to this one and is known to be integrable. Of course, I'm talking about one loop integrability at this stage. And but it's actually, this is totally equivalent to this, so if this is higher loop integrable, so is this. Just more difficult to show. So this reduces to the usual cases, but in general doesn't satisfy the co-cycle. Do we get a quasi-Hopf algebra? Well, to check this, what we need to do is construct this coassociator. And let me just give you an indication of how this is done. So how do I make sense of an expression like this? Well, the problem is, we have a coproduct and it's acting on the twist. Now the twist is this thing here. Right? Now, how do I act with a coproduct on the twist? That's what this tells us. So we have phi. Phi is the original coassociator. For n equals 4, that coassociator is 1. 1 times 1 times 1. It's 3 times the identity meter. Because it's a trivial associative co-algebra. I mean, the co-associator is trivial, because it's just a Lie algebra. So what we need to do is act with 1 times the co-product on F. F being that twist. Now that is, the problem with that is that we only know how to act on algebra elements. And that F, that twist, is not an algebra element. It's at the level of the group, not at the level of the algebra. So what we need to do is first write it in exponential form. And you can kind of see, I'm going to give some explicit examples later, but for special cases. But there are 4 parameters: real beta, imaginary beta, real H, and imaginary H. We chose to label them like that. So you need to write F in this form, where these are the classical R matrices. So classical R matrix is what you get, the classical twists, but these are related to the classical R matrix. So basically it's what you get if you expand your twist to first order, then you get this classical twist. And they all appear here. So if, for instance, I look at the real beta, then all these are gone, And this actually will turn out to be just some product of the Cartan elements of SU3. So something like lambda 3 wedge lambda 3 times lambda 8, if you think of Kelman matrix. So it's something diagonal, and you can easily exponentiate it. Well, this would be actually I beta, and then you get the real beta twist, which was, of course, has been known for a long time. So these are the classical twists. Alphas are known functions of Q and H. So we've done this, and knowing this, we can compute this. And how do I do this? Well, a twist it lives in two copies of the algebra, and the nice thing is that this thing actually exponentiates. So what this does is this goes up in the exponent here, and it doesn't affect the first copy of the algebra here, it affects the second copy, and it gives you, then you apply the standard SU3 twist, because these are, of course, the antiform. So this coproduct is the antiform coproduct. So this just gives you, x times identity plus 1 plus identity times x. I'll give an example. The problem is this is very complicated, and the reason this is not out yet is because we're trying to simplify it so we can actually write it in LaTeX, because it's actually quite a large expression in general, if you look at all these four terms, all these four classical twists. And there might be a better basis, but we haven't found it yet, than using this particular way of writing it. But what one can check explicitly if we plug in some special cases, and also numerically for the general cases, there's this quasi-Hopf. The Baxter equation is satisfied. So we do, of course, this is just double checking because it's the twist construction by itself tells us we should get the quasi-Hopf algebra, but this is just to make sure that we understand and we haven't made a mistake somewhere that this is actually something. So to give an example of how this works, let's look at imaginary beta, which is kind of a simple but non-trivial case. So Q bar is Q in this case, because remember Q was e to the I beta, so if beta is imaginary, then Q is real. And so you have this, and the H's are 0. F, the twist that I wrote, can be written in exponential form like this. I'll give you alpha in the next slide. I haven't told you what alpha is yet. But you can see that these are the Gell-Mann matrices. So this is basically, some combination of the Gell-Mann matrices. And you can see this is not going to be a diagonal thing. Wedge means just this. And now when I act with identity times the coproduct on F, well, this actually exponentiates, and what you get is, the coproduct acting on the second term. So you're right, this is 6 terms because of this. There's 6 terms, and for each one of them, you write the coproduct for the second term, and then the coproduct of lambda 2, we know what it is. It's lambda 2 times 1 plus 1 times lambda 2. So what you get here is a 27 by 27 matrix, because now you have to unexponentiate this, like do the exponentiation basically, and it will give you a 27 by 27 matrix, which is has the right dimensions to be identity times delta times the twist. You can do the same thing for delta times identity, and from that you apply this. These are trivial things. This is just the twist, but acting on the 1, 2 or the 2, 3. But the non-trivial parts are the ones in the middle, and you can get the coassociator, and after you do all that, then you get some expressions for it. So it's a 27 by 27 matrix, but it's much easier to write it in tensor form. So basically this acts on 3 copies of the algebra and gives you 3 copies of the algebra. So instead of writing it 27 by 27, you can write it as a 6-index tensor. And these are some of the many components it has. And you can see it's fairly complicated. And I'm using everywhere this alpha of Q, which is the arc cos of this combination of Q. So this is still for imaginary beta, which is real Q. So Q is a real parameter here. And which can be expanded, of course, in some nice way. I'm not going to go into the details. Just to give you an indication, these are hybrid formulas because I'm using Q, but I'm also using alpha. Okay. Now, it could be interesting to see if I can just plug in, but you can see already if I want to plug in Q equals -1, it's maybe kind of a special point. I'm not sure how things are going to work out. I mean, I am, but still, it might be worth checking the statistics. There. Okay, so why is this good for anything? What we can do is we can define a star product, and I'm interested in deriving a star product not on the algebra itself, but on the module. And my module is what the algebra is acting on, and the algebra is acting on the scalar fields of n equals 4. So the phi 1, phi 2, phi 3. So compatibility between the Hopf algebra G acting on, this means acting on its representation space. So if you take the product of two representations, then there has to be some compatibility argument, which tells you there's actually a unique way of defining a star product. This is kind of deformation quantization stuff, which I'm kind of very quickly going through. But what you find is that actually, if these are modular elements, so think of them as the scalars of n equals 4, phi1, phi2, phi3, because I'm acting on the fundamental representation of SU3, and that is the 3 scalar. So the product of those actually gets twisted by the same twist that you twisted the algebra with, and that allows you to define a star product. And again, I can give you some explicit expressions. If you write this star product in index form, you use that same twist, but you just sum over, there's some particular kind of rotation that you do. And what you can show, which is quite nice, is that I can write an expression like this, which is the Leigh-Strassler. One way to think of this expression is as the vacuum manifold of the Leigh-Strassler theory. So if you do the F-term conditions, you would get this thing, okay, without the star. Now, if you put the star in these conditions, also here, if you put the star here, then you get something proportional to the n equals 4 story. So you can rotate, you can basically untwist the Leigh-Strassler any expression, but this is just a particular expression, any expression in the Leigh-Strassler theory to the n equals 4. Now, this is of course at the level of just SU3. What does it imply about my scalars, which are not only representations of SU3, but also, of course, they are matrices of SUN of my n equals 4. Actually, it turns out that this is totally compatible with the SUN structure. And I can directly take these things and convert them to scalar language. So now, these are the actual scalars of n equals 4 experiments. While here they are the scalars of the Leigh-Strassler theories. The star product takes us between these two. So I have a way of kind of undeforming my Leigh-Strassler and getting back to the n equals 4 case, which is very similar to the star product that Leigh and Mandelstam introduced to undeform or deform appropriately the real beta and relate it to n equals 4. And that was crucial in their language in order to develop their TST approach. So that's Moyal's star product that they had. It's a very, very special case of what we're talking about. So if you take this to be the real beta, Q is a phase, H equals to 0, this is just a Moyal. I mean, not technically the Moyal, it's the star product of Leigh Mandelstam, which depend on the charges of the scale. Now the question is what happens at the cubic level, because that was quadratic, so this is the quadratic star product. You might expect that at the cubic level things get a little bit messy because of non-associativity. And indeed that's true. You have two possible cubic expressions. These are still, you should think of these as the scalars of n equals 4, but now I'm multiplying the first two times the third, or here the second two times the first. In the same order, but different placement of parentheses. These expressions are not in general the same. And you can, we call these the left, the parenthesis on the left, we call it f cubic left. Parenthesis on the right, we call it f cubic right. And there are some expressions for them that you can find. E to the minus f is just code for exponentiating the classical twist. And for imaginary beta, where things are still kind of reasonable to show, you get various expressions. There's many, many more. I'm just giving some sample. They also depend on this alpha parameter, which was this arc cosine of q minus 1 plus some stuff. This is non-associative. You can see it already here. You see there's an element, say 1, 1, 2 for the left, and there's a 1, 1, 2 for the right, and you can kind of see they're not the same. You have different expression. So this is if you write these explicit things out, you'll find that okay, these don't match. However, as argued, the coassociator should relate the two placements of parentheses, and that's actually true. So the coassociator I exhibited earlier. There's a way that you can understand how it. Actually, that's the definition of the coassociator. It's what relates these two placements of parentheses. Okay, this is maybe a slightly complicated expression, but you can think of it at the level of indices that I talked about earlier. There's also an inverse star product you can define, which actually I think is the most useful star product. So basically, instead of defining the star product with f, I'm defining with f minus 1. So the original star product was defined here, and it was actually defined in terms of f minus 1. The inverse star product, unfortunately, is defined in terms of f, not f minus 1. And you can see it here, it's f acting on this. And if you write it out, it's something very simple like that. So take the twist, the one I showed you, and start deform your coordinates of your C3, of your, the thing that SU3 is acting on. And what that does is actually exactly the opposite. It takes an n equals 4 expression, so this is the commutator, of say a commutator in n equals 4, put a star there, and you get an expression in Leigh-Strassler theory, up to some constant, up to some value. So this is the exact thing which is the analog of Lunin and Maldacena. What they did is they took n equals 4 expressions, they added a star, and they got the real beta expression. Here I'm generalizing that to the general Leigh-Strassler theory. And yes, theoretically you can basically say that I'm taking the normal commutator and I'm deforming to QH commutator, which is exactly this, of course up to some constants that probably play a big role, but I'm more interested in the structure of this. Now, one of the beautiful things is that even though this cubic product is, at the cubic level, I'm not giving all the details again, but for this asterisk product, the inverse one, of course it's still non-associative. However, if you write down a cyclic relation, then it turns out that this coassociator that should be there, but I'm using phi for two things, so I hope that's clear, the scalars and the coassociator. But phi actually drops out of cyclic relations you can write down. And what that leads to is that I can write the n equals 4 superior Mills superpotential, that's the first line here, before I take the trace. So you see, well, I have 6 terms, they're all the cyclic permutations that enter the n equals 4 superpotential. I add a star, and that gives for me the n equals 4. That's after taking the gauge theory trace, because everything is cyclic, so terms combine nicely. This is n equals 4, but with a star, that is equal to the asterisk, that's equal to the general Leigh-Strassler potential, just multiplied normal. Okay? So why I find this useful is that it gives me a way of taking an expression n equals 4 and getting an expression in Leigh-Strassler theory using the symmetry, using this twist. We can also show, I haven't talked about this, this is also some slides that I kind of removed. You can also show that the kinetic terms are not deformed by this. Now, to discuss this question is slightly involved because you have to, everything here was holomorphic, and I was working with SU3 acting on Z1, Z2, Z3. Now you have to define what we call anti-holomorphic quantum plane relations and mixed in order to be able to attack this problem, but there's a consistent way of doing it and it works out. If you star multiply phi bar phi, of course this is a sum. If this were not a sum, it would not work. So phi 1 star phi 1 bar star phi 1 is not equal to phi bar 1 phi 1, but if you add all three of them, everything kind of cancels and this becomes this. What this tells us is that I can take the Lagrangian of n equals 4 superior Mills, put a star everywhere between the fields, the kinetic term, which of course is like this, and the gauge field doesn't know anything about this because it's not charged under SU3. The kinetic term stays the same, the superpotential is going to be deformed. Okay, so the Leigh-Strassler theories in our current understanding are just these asterisk deformations of n equals 4, as long as you're willing to accept that, okay, you have the star product and it leads to a quasi-Hopf algebra in general. Now, why is that perhaps useful? Well, one thing that we did in the paper in 2016, but for a very special background, was we tried to see how can you start from the dual background of n equals 4 and get the corresponding background for the deformed theory. And the approach that worked best for us was to consider, okay, this is a very quick slide. If you know about generalized geometry, then you can follow, otherwise you can look at the paper or ask me afterwards. But in the generalized geometry framework, one encodes the background in terms of two pure spinors, which are wedges of, one of them is like the holomorphic form for the Leibniz, and then there's this phi plus, which is the kind of exponential decaler form. I've skipped many kind of introductory slides here. And flat space is just, this is what we usually call omega, this we would call e to the ik, where k is the Kähler potential. And now the claim is that you can take those, you can take flat space, add star products, and you get the corresponding pure spinors of the deformed background. Now let me say a couple of things about how I'm thinking about this. This is in the context of, think of a, how much time I have? But 5 minutes? Okay, that's perfect. This is more or less my last slide. But I'm thinking in the sense of a D3 brane with a transverse C3, right? So what I'm doing here is I'm Q-deforming my C3. C3 is the space of the three scalars. And of course, the z's are abelian coordinates, but of course on the D brane, these are going to become non-abelian scalars because it's actually not one D brane, but it's the stack. Right? So what I'm doing is I'm deforming C3 to a QH version of C3. And what we found for that specific case, which actually was the case where Q is 1 plus W and H equals W, that's an integrable case, we found that doing this deformation led to a solution, an N equals 2 smooth supergravity solution, which now is exactly a cone over a deformed S5.
So this product is like having a B field on the S5. That's it. That's sorry. Is this thing similar to having a B field on the S5?
It's exactly that. Yeah.
Okay.
So we're turning on not only B field in general. So what happened is, if you think of we prefer to think in two steps. First, we think of the transverse C3 to the stack of branes, and you do the deformation there. What you get is only a B field. So it's an N equals 2 background. But then you need to take of course, now you need to take the near horizon limit, and what you get there is actually that, if you actually take the near horizon limit and follow the usual procedure and kind of self-consistently solve supergravity equations, so at that point we kind of gave up on generalized geometry, we had to actually solve the equations. We also got the C field, like we got all the Ramond-Ramond. Because of course this is going to lead to Ramond-Ramond phi forms and all that. The phi form is exactly the same as in the N equals 4 case, but there's going to be a C3. There was no action. And so basically we got this dual background, so the deformed sphere, by applying this approach, this two-step approach, and we kind of, we think of it as doing TST, but without doing TST. Because what we're doing is we start multiplying the pure spinors, these are called pure spinors, of flat space, and then taking the near horizon.
So this effective B field that you get might be complex if Q is something random, or?
Yeah. Well, you mean complex as in adding the C field part and having this generalized G, or
complex in the sense that it's not a real flux.
No, but I mean, if it's complex, you write it as, in the usual sense, like it's, you combine the...
No, I don't mean it by that. No, I don't mean that.
No, only, because these are actually consistent supergravity backgrounds, so... No,
but I'm asking whether it's unitary or not, so this is the question I was asking.
Yes, okay.
So whether you need complex fluxes to support it.
Yeah. So our construction was special because we were only using this integrable case, because we did not want to bother with non-associativity, because this is an associative case, and we did not, I don't have the answer for the general case, but in the construction there's nothing really, because everything here is complex. I mean, you can do an arbitrary Q bar deformation here. By the time you get to the level of the actual type 2B solution, everything is the way it should be. Like the B's are real field, and there's the three-form, the two-form Ramond-Ramond potential, and so on. So, because even though everything is complex at this level, the construction, which I'm not giving, leads to a normal type 2B background.
Okay.
There's nothing non-unitary as far as we can see. But the point about this is, of course, that's actually one of our motivations, is we're claiming that the CFT has this new quantum symmetry, right? That it's actually, instead of thinking of just having some Z3s, we should think of this quasi-Hopf algebra, Now, how does that manifest itself on the gravity background? Of course, the gravity should be just a smooth, normal, like it's expected that these theories have normal type 2B duals, which are some normal deformation of S5, not something complex and all that. So we showed it in all detail for this W deformation. We also showed it for Lully-Maldacena, so we can do Lully-Maldacena without using TST, just the star product. It's equivalent though. But we have not figured out how to do it for the general QH. The reason being non-associativity, so there needs to be some new ingredient here, because, or at least you need to know the starting point very, very well. Because now I need to start putting parentheses here if I'm going to deal with a non-associative algebra, and we don't yet know how to do it. Okay, now before I conclude, let me say about unitarity. Well, these quasi-Hopf algebras have been studied for a long time, since Drinfeld, and there's a paper from '92 by Mack and Someros, which explicitly studied unitarity for doing, like, thinking of these as, it's a kind of maybe Coleman-Mandelstam type argument, but what is the most general such quantum group that you can deform your Lie group, your normal Lie group symmetries by, and still preserve unitarity. And what they got was something called a weak quasi-Hopf, weak quasi-triangular quasi-Hopf algebra. And this is a special case of that. So we believe that in terms of unitary, at least we are covered. That even though we're doing a quantum, like we're thinking of this as a global symmetry, the theory, but it's not a Lie algebra symmetry; it's a quantum group symmetry. But it seems that it's compatible with the way that you would want to define your statistics properly for bosons and fermions. And just make sure that everything is consistent. But I do not claim to have a totally full understanding of it at this stage. Anyway, to conclude, we found a twist which relates n equals 4 to Leigh-Strassler. We're claiming that we're not breaking the SU3, we're just deforming it. But still should be the same number of generators, but now the generators of a quasi-Hopf algebra. Any expression in Leigh-Strassler can be related to n equals 4 and backwards. And so we can relate the Leigh-Strassler potential to the n equals 4 by just adding an asterisk star product to this to n equals 4 case. In terms of outlook, well, of course it's important to study, does this imply anything about conservation laws that we haven't really studied yet? If we're claiming that we're not breaking the SU3, we're just deforming it. Of course, there's quantum groups, and there's some understanding that I'm currently lacking about to answer this question. Noether's theorem and all these things. Should we revisit non-integrability in these cases? Is there a way to prove why integrability breaks down? Because quasi-triangularity is still there, but where in the algebraic Bethe-ansatz, for instance, computation, does integrability break down? It's not totally obvious to me where exactly that happens. Is there a quasi-Hopf symmetry on the dual gravity side? If that's true, then maybe it will be useful in terms of constructing the dual backgrounds. And that's one of the main future goals, extend these results. This is the paper with Dlamini, to extend, which was for this special case, which we call the double deformation, can we do it in general? Can we relate this to other solution generating techniques, which are more from the sigma model side, rather than just from this quantum group perspective? And perhaps, if this is established, is there some deeper reason for it? For having these quantum algebras there? Does it mean something that these perturbatively finite theories have this group, quantum group algebra it's a classical symmetry of their potential. That's the way we want to see it. And of course, you can ask quantum questions here, but we haven't really gone there yet. But anyway, we were hoping that perhaps in the same way that quantum groups appear in 2D CFT, perhaps far down the line, one can establish something similar for 4D superconfirmable field theories, that perhaps there is some quantum group behind. Because definitely this is not about integrability. Integrability is supposed to be broken, so what else is there that this is responsible for, this quantum group symmetry? So we're studying some other examples as well, n equals 2 theories, for instance, and trying to see whether any of those might have some variation of these Hopf algebra symmetry present. Okay, thanks a lot for your attention.
So, give more questions, comments?
So this deformation will not be integrable. It's not like you're hoping that you can do something with the quantum groups to
I mean, that's the thing. I mean, it would be nice to actually figure out where the integrability is broken, if it's broken. I mean, we have already looked at the, say, imaginary beta from the perspective of this analytic non-integrability, and we found that there are strings that are non-integrable. You can find chaotic motion for strings, and this is like fully planar limit, you know. So
from the one loop perspective, we can just write down the one loop Hamiltonian, this whatever 9 by 9 thing, and I assume it's well known.
Yeah.
What is the most general integral matrix of that kind, right?
Yeah.
And then you can check whether this falls there or not.
So this was studied. There are these Zamolodchikov's conditions, which are slightly more general than doing the Yang-Baxter. Because like in Yang-Baxter, it's clear it doesn't satisfy Yang-Baxter.
Of course.
But there are these Zamolodchikov condition as well. And Teresa Monson, I think with Bunzik, back in the mid-2000s, about 10 years ago, they studied that. And they came up with a list of what are the integrable cases.
Yes.
Which are, for instance, this double deformation is directly from their paper.
Okay.
And so it's real beta and things which are unitary related to real beta, more or less. So
integrability will break down. It's not like it's not that there's a more sophisticated way of thinking about the problem that will.
No, but I mean, but the question is somehow what is happening here. Obviously, if you don't have Yang-Baxter, there's something non-local happening because we have this quasi-Yang-Baxter, right? So it seems that there is this coassociator, which you cannot think of it as a two-point scattering anymore. So in that sense, integrability cannot be there. But you still have this more general Yang-Baxter equation, and maybe you can still get somewhere. Maybe it's not integrability in the traditional sense of momenta being permuted. But I have not seen in the literature any discussion of, maybe it's my own ignorance, but I don't know what is known about integrability in relation to quasi-Hopf algebras. So it might be some non-associativity is of course always something we try to avoid, but I could not pinpoint where in this argument integrability is specifically broken. There is, it seems to be some interactions are in a way non-local because you have these two-point interactions, but at every time you have to insert these files, which contain some other information.
Yes.
But all that takes us to the point I made in the beginning, that I do not have a spectral parameter, so I do not have a dynamical Yang-Baxter, and I don't know what would be the dynamical, quasi-Hopf Yang-Baxter thing. So if these things eventually can be made to work, then I'll be closer to answering that question. At this stage, it's more at the level of what is the symmetry. So it's like saying I have a Lagrange that has SU3 symmetry. Now it has this quasi-Hopf symmetry. Now SU3 is not what gives me the integrability, and it's part of the story. But you actually there's much more happening there, and I think one needs to study that in more detail.
Okay. So then,
Maybe mention what is the, if you mentioned it and repeat it, what kind of deformation of the files given is the base of that code? Is it known or in which cases or?
Okay, so if I was to take just Q equals e to the beta, right? Then this should just be the Mandelstam. So this should be 11.
No, but when you turn it on H also as well.
Yeah. So it's.
No,
we have the metric. We have explicit everything. It's an n equals 1 background. I mean, we can. The full thing is ATS5 cross this deformed S5. So we could explicitly construct both n equals 2 and n equals 1 metric. Sorry, what I mean is the deformation of C3. Then we added a deep-brain that broke to n equals 1, and we found the corresponding ATS5 times S5, call it double that. So that's an explicit metric. It's smooth, but the thing is, it's because these theories are unitary related. So this is unitary related to that by just taking the scalars phi1, phi2, phi3, and rotating them by a matrix times the same. So and we can actually do the same and show that this is diffeomorphic to the model.
You are not learning anything.
No, we did not learn anything new. It was just maybe a consistency check. because we were not, for Drinfeld Twists it's kind of too trivial. I mean, the deformation you're doing is just cartons in the SU3, and it's kind of simple. Here, when doing the double deformation, we do not really use any information about, like demands. It was just adding the star product to the pure spinors. But in the end, what we got was diffeomorphic to Drinfeld Twists. So if the metric is insanely complicated, we wrote it all down, but you can write it on a few pages of LaTeX. But it's complicated much more than Drinfeld Twists, but there's diffeomorphic to it. As it should be, because these theories are not really just a very complicated basis that you've redefined your scalars to something. So the hope is that perhaps these techniques will eventually allow us to do the same for these more general theories, which are not expected to be the same as Drinfeld Twists. There are quite a few problems in trying to do that. At the naive level, what we can do is we can reproduce the results of Colaxisi from some time ago, which was the second order. So if you keep these separate, Q and H as being independent, there are results up to second order in this H parameter. For instance, take Q to be 1 and H to be something. There are results up to second order, and we can reproduce those. So definitely we're correct up to the level where non-associativity takes over. Because then we have to be more careful, and we don't know exactly how to be more careful. Like, how does the coassociator enter that procedure that I talked about earlier? Or, how basically it's a question of the starting point. What is the correct starting point? I have a cubic pure spinor, but nobody has given me the parentheses. And maybe it's just a matter of placing the parentheses correctly in order to deform. It's like the usual question. We start with a classical expression. What is the correct quantum expression? There's many quantum expressions that reduce to the same classical one. And I think we have the same problem. But imaginary beta, we know the answer, because you can get it by SL2R. So we're hoping to first understand this for imaginary beta, because we know what the background is, and then we can try to work backwards and figure out how that happens. And if we do that, then maybe it's not a big jump to understand the general H.
Okay, so then let's thank Costas again.